To solve physics problems on Isaac Physics and elsewhere, it can be useful to use the following steps in order. Draw a diagram or several diagrams of the situations throughout the question. Think about what the relevant pieces of information that you need to use are. Try to avoid cluttering your diagram with lots of unnecessary information. Analyze the problem. What's the goal? What physics concepts will you need to use? And think about what other information you can extract from the question. Then, plan how you're going to solve the problem. Think about the concepts that you just looked at and what you can work out using them. You may also want to consider what equations might be useful. Then, you can implement your plan and solve the problem. Once you've got an answer, you can verify it. Check that you found what you were looking for. Are the units correct? And does the answer make sense? If you get stuck, don't be afraid to return to an earlier step. Sometimes you'll start going down the wrong route, and that's okay so long as you realise this and try something different. I'm now going to use this process to work through a problem from Isaac Physics. The problem's energy of a bullet from Dynamics Level 3. The first thing to do is start by reading bits of the question and begin to analyse them by drawing a diagram. Start by looking at the preamble and splitting it up into little pieces so that each little piece can be added to the diagram. This allows us to set up our initial situation. This preamble also contains some information about the situation after the collision has occurred, so we'll need to move this out of the way and separate the diagram out into before and after the collision. Although this just says and remains embedded in it, it's actually giving us a few pieces of information, not just the position of the bullet, which is now embedded inside the block, but also the fact that they're moving together and therefore have a joint velocity, which I'm labelled here as v. Even though at the moment we don't know which direction the bullet and block will move, I've drawn it in as going to the right here, because if it turns out that the correct answer has it going to the left, this will simply show up as a negative value for v later on. We can now read the goal of the question and use this and the diagram to analyse what physical concepts we might need to consider. The goal is to show that over the course of this collision, the loss of kinetic energy is of the form half k times the mass of the wooden block times the mass of the bullet, where k is an unknown in terms of the speeds and masses given. From the goal and the fact that the bullet is staying embedded in the block, we know that kinetic energy is not conserved in this collision. It is an inelastic collision. However, momentum is conserved in all collisions, so that the momentum before the collision is equal to the momentum after the collision. We can now use these concepts to explore the question. We know that the kinetic energy of an object is given by half mv squared, so we can use this to look at the kinetic energy before and after the collision. Before the collision, the kinetic energy EB is equal to half little m little u squared plus a half capital M capital U squared. After the collision, the kinetic energy EA is equal to half multiplied by the sum of the two masses multiplied by v squared. We also know that momentum is conserved. Momentum is a vector given by P equals mv for an object. So in order to use the law of conservation of momentum, we need to choose which direction we're going to use as positive. Taking to the right as positive, the momentum before the collision is given by little m little u minus capital M capital U. The minus sign is because the velocity that we've drawn on capital U for the wooden block is acting to the left. The momentum after the collision is given by the sum of the masses, little m plus big M, all multiplied by v, because as we've drawn it in the diagram, the velocity v is acting to the right. We can use the equations we've got for the kinetic energy before and after the collision in order to work out the change in kinetic energy, which is EA minus EB. This is equal to half little m plus capital M all multiplied by v squared minus a half little m little u squared minus a half capital M capital U squared. We can also use a conservation of momentum in order to equate the momentum before and after the collision. This gives little m plus capital M all multiplied by v is equal to little m little u minus capital M capital U. We can see that we have an unknown v in our equation for the change in kinetic energy and in our momentum conservation equation, so we only need to plan how we're going to find v. We can do this by rearranging the momentum conservation equation to make v the subject, and we can substitute this into the equation for the change in kinetic energy in order to solve the problem. We can then implement this, which gives us v equals little m little u minus capital M capital U, all over little m plus capital M. Then I can substitute this into the equation for the change in kinetic energy, so that I've got this purely in terms of the masses and initial speeds, all of which I know. What we have now is technically the answer, in the sense that we could put numbers in for all of the variables here and actually get a change in kinetic energy out. However, in this format, it's very hard to understand anything by looking at it. So we expand it all out and simplify. As well as cancelling out where we can, we also make sure that the denominator of all the terms is the same, so that we can add or subtract them all together. At the end of the simplification, we also need a quick trick. We need to notice that the term in the brackets in the numerator is just the sum of the speeds squared. Now that we have a simple equation for the change in kinetic energy, we can look at it and check it to make sure that we've not made any mistakes in our working out. Firstly, you can see that we've got a minus sign here, which means that kinetic energy has been lost in the collision, which is what we expected from the question. We also want to check the units of our answer. Working this through, you can see we've got kilograms multiplied by kilograms multiplied by speed squared, so that's meters per second all squared, and divided by kilograms here. We can rewrite this as kilograms times by meters per second squared times by meters. So we've got a mass times by an acceleration, which is a force given in newtons, and then that's multiplied by a distance in meters. Force multiplied by distance gives us work, which is measured in joules, which is the same as a change in kinetic energy, so the units work. We can also just take a look at the equation that we've got and see whether it intuitively makes sense. We can see here that we've got a term of u plus capital U. Since in our diagram we defined velocities as in opposite directions, so that the bullet and block of wood are moving towards each other, u plus capital U is in fact the relative speed of one of the bullet or block with respect to the other. This means as this relative speed gets bigger, the amount of kinetic energy lost in this inelastic collision increases. This makes sense, as if there was no relative velocity between the two, you wouldn't expect there to be any kinetic energy loss. You should take care to verify your answer whenever possible. Now that we're happy with the equation we have for the change in kinetic energy, we can compare it to the equation given in the question for the loss of kinetic energy and work out what K is. This equation can then be used to solve the numerical part of the question by substituting the bullet's mass and speed and the block of wood's mass and speed before the collision into the equation. Of course, we mustn't forget the units. As this is a kinetic energy, the units are joules. We also need to be careful of the number of significant figures we use. Both the mass and the speed of the wooden block are given to two significant figures. The speed of the bullet before the collision is given as 400 meters per second. Using the sight rules, all trailing zeros count as significant figures, so this is 3 significant figures. But the mass of the bullet is again given to 2 significant figures. This means that we can only give our answer to 2 significant figures, giving us a final answer of a loss of kinetic energy of 1,600 joules. Try using this method to solve other physics problems. Draw a diagram, analyse the problem, plan how you're going to solve the problem and implement that plan, and afterwards verify your answer to check that it makes sense. Remember, you can always go back to earlier steps, so don't be afraid of doing this. Good luck and enjoy isaacphysics.org.